In today's lesson, we are going to be looking at the exponent laws. So in our previous lesson, we looked at negative exponents and the zero exponent. Now we're going to be look at some laws where what happens when we start incorporating operations into our powers, with our exponents. There's going to be three laws that we look at. The first one is called the product rule. And the product rule is when we multiply powers. Right? So when we multiply, the answer is called the product. So that's why it's called the product rule. So we have an expression, 2 to the power of 2 times 2 to the power of 3. Let's write that in expanded form and then see if we can simplify it to a single power. Well, 2 to the power of 2 is just 2 times 2. And we multiply that by 2 to the power of 3, which is 2 times 2 times 2. And what we should see is that we just have a long string of 2's being multiplied together. So I can rewrite this as a single power with a base of 2 and an exponent of 5, because I have 5 2's being multiplied together. Let me use just a different color, just so we kind of keep all different. If I look at the next one, 5 to the power of 3, well, that's 5 times 5 times 5. And if I multiply that by the next term, or 5 times 1, or 5 to the power of 1, which is just 5, this is my expanded form. I can simplify that as a single power of 5 to the power of 4, because I have 5 times itself 4 times. And if I look at the final one, 3 to the power of 5, that's 3 times 3 times 3 times 3 times 3, and then multiplied by 3 to the power of 2, which is 3 times 3. It's all a bunch of 3's together, so I can put this long string together and write it as a single power with a base 3, an exponent of 1, 2, 3, 4, 5, 6, 7. So 3 to the power of 7. Now, when we're dealing with these expressions, we don't want to have to expand them every time we want to write it as a single power. So is there a quick way that we can go right from the expression to the single power? Right? Is there a way we can go right from the expression to the single power? Is there some relation between the expression and the single power? And what we should notice, and we want to focus on the exponents in this case, if I have two powers and they're multiplying each other, I can just add the exponents and get the same answer. 2 plus 3 gives us the exponent 5, 3 plus 1 and 4, 5 plus 2 is 7. So my rule, or the product rule, when I multiply powers, I keep the base the same. So a to the power of m times a to the power of n. The base stays the same as a, and the exponent is m plus n. Now, one thing to keep in mind, in all of our expressions, you have to have the same base. This only works because it's the same base, so it's the same long string of numbers being multiplied by itself. If I had two different bases, I wouldn't be able to simplify it to a single power. So that's going to apply for actually all of our rules, but we'll write it down with each one. Right? You have to have the same base, and every example we look at is going to have the same base. So for example, let's simplify and then evaluate. So simplify means write as a single power. Evaluate means what is the value, right? So if I look at the first one, 4 to the power of 2 times 4 to the power of 3. We just said our product rule states that we add our exponents. So this becomes 4 to the power of 2 plus 3. which is 4 to the power of 5. So this is my simplified form. So when I simplify, that's what we're talking about. The next step is to actually evaluate it. And if I plug 4 to the power of 5 in my calculator, I get 1024. This answer is the evaluated answer. So it depends on what the question's asking. If it's asking you to simplify, it means write it as a single power or as much as you can. If it's evaluate, then it means tell us the actual value. Now, you may not have to show this stage here, right? You may not have to show the 2 plus 3 because you know what the rule is, which we just learned. So you don't have to show this step. It's okay if you just jump right from here to here. Now, when we get into some more complicated ones, it would be beneficial and it is recommended and I don't want to say mandatory, but it is crucial that you do show the in-between steps so you don't miss anything. So 4 to the power of 2 times 4 to the power of 3. We add the exponents, 4 to the power of 5. The base stays the same. We haven't changed it. And then we evaluate it to 1024. For B, same idea. We have a power times a power. The base is the same. So I can rewrite this as negative 2 to the power of 4 plus 3. Again, this step may not be necessary. I'm just showing so you can see how we get to our final answer. So we get negative 2 to the power of 7. Again, this is the evaluated form or the simplified form. The evaluated form is I'm going to actually plug this into my calculator and I get negative 128. Now, one thing to keep in mind, we want to use brackets with negative bases. Right, so when we have a negative base, we want to make sure we use brackets when we're evaluating it. Some calculators may not incorporate the negative unless you put the bracket in, and that can be a factor when you have an even power or an even exponent. So what I mean by that is if you had negative 2 squared, that should be negative 2 times negative 2, which is 4. If you don't put the brackets in, your calculator may not include that negative when you square it. So they may think it's 2 times 2, which is 4, and then the negative is still there, so it's negative 4. So it depends on what the question's stating, but in our case, if we have a bracket around the base, we want to make sure we include it. Let's do 2 more examples. 3 to the power of 2 times 3 to the power of negative 5. Again, simplify, we want to write it as a single power. So 2 plus negative 5 or 2 minus 5. Right, so we still keep the same signs in the exponents. So 2 minus 5 is negative 3. General rule of thumb, we want to write our powers with a positive exponent. So as we learned yesterday, I need to flip my base. So it becomes 1 over 3. All to the power of now positive 3. So that's my simplified form. The evaluated form is, okay, tell us what this actually works out to. And we said yesterday, this 3 can apply to both parts. So 1 to the power of 3 is just 1 over 3 to the power of 3, which works out to 1 over 27. So 1 over 3 to the power of 3 is my simplified form. 1 over 27 is the evaluated form. D is a little bit different because now we have coefficients or numbers and powers, and they're not combined, right? They're 2 separate things, right? So the number is different from the actual power. So that exponent 3 does not apply to the 2. It only applies to the x. Same with the 2, it doesn't apply to the negative 5. Now, when we're dealing with questions like this, we want to focus on the parts that are the same. Now, I've already kind of gone through and helped us with that because I've highlighted the parts that are the same. The two coefficients are the same, and the two powers are the same. They both have a power or are powers with base x. Now, a different way you could write this. So this is going to be kind of a longer explanation, right? But if I look, if I look at 2 and then x to the power of 3, there's actually a multiply or a multiplication in between those two. Same between as the negative 5 and the x squared. So realistically, if I wanted to rewrite this, I could say 2 times x to the power of 3 times negative 5 times x squared. 4 different things being multiplied. Now, with multiplication, order doesn't matter. So I can actually rearrange this, and I can say, well, I can do 2 times negative 5. I can put my two numbers together, and I could put my two powers together. My two numbers I can multiply no problem. 2 times negative 5 is negative 10. X to the power of 3 times x to the power of 2, well, my power rule says I add those exponents. So x to the power of 3 plus 2, which gives me negative 10 x to the power of 5, which is my final answer. This is my simplified form as well as the evaluated form. I can't evaluate this any further because I don't know what x is. So this is simplified and evaluated. Now, you could skip right from the beginning right to the end. Right? Multiply your two numbers together. 2 times negative 5 gives us negative 10. X to the power of 3 times x to the power of 2. We add the exponents and we get x to the power of 5. We can't combine the negative 10 and the x to the power of 5. We can't merge that together to make one single value. So I leave them kind of together but separate. So you could just jump like that. That means that all this stuff in the middle, all this stuff here, is not really necessary. I'm putting it down so you kind of see the step-by-step process, see why we're allowed to just focus on the individual components, right? Or focus on the identical or similar terms or similar values or parts. So when you have a coefficient or a number and a power, or a number and a variable, focus on similar parts. So I'm just going to make a small note on that. And the highlighting will really come in handy here because we're seeing the different, or because it helps identifying the different parts. The next rule is the quotient rule. So the quotient rule is basically when we're dividing powers. So quotient is basically the answer to when we divide two things. So the quotient rule is for dividing powers. Now, if I was to write this out, so I have 4 to the power of 5 divided by 4 to the power of 3. If I was to write that out in expanded form, 4 to the power of 5 is the same thing as saying 4 times 4 times 4 times 4 times 4. I'm going to write this divided in a different way. I'm going to write it as a fraction, so I'm going to divide that by 4 to the power of 3, which is 4 times 4 times 4. That's the expanded form. Now, if I want to write this as a single power, can I simplify this expanded form? It's a little bit different from the other one, but I can actually simplify this because if I have a number on top and I have the same number on the bottom, right, or if I'm multiplying by numbers on the top and numbers on the bottom, they can cancel out. Because if I multiply by 4 and divide by 4, they will cancel out. Actually, let me use a different color. So I can cancel out a 4 on the top, a 4 on the bottom, and continue through until I'm done. Now I'm left with just 4 times 4. What is that as a single power? Well, that is 4 to the power of 2, or 4 squared. You might already be able to figure out the rule, but let's go through the other examples and take a look and see what we get. So 7 to the power of 4 is 7 times 7 times 7 times 7, all divided by 7 to the power of 1, or just 1 7. I can cancel out with 7 on the top, a 7 on the bottom. That leaves me with 7 times 7 times 7, which as a single power is 7 to the power of 3. Let's look at the next one. 2 to the power of 7. So that's 2 times 2 times 2 times 2 times 2 times 2 times 2, all divided by 2 to the power of 2, or 2 times 2. Let's cancel out what we can to simplify. So cancel out 2 2's on the top, 2 2's on the bottom, and we end up with 2 times 2 times 2 times 2 times 2. Let's move this down a little bit. So that simplified works out to 2 to the power of 5. So again, our goal is to go from the expression to the single power, right, from here to here. I don't want to have to expand it every time, cancel out, and then write my single power. So what rule or what kind of shortcut can we do going from the expression to the single power? Again, similar to the quotient or the product rule, we want to focus on the exponents. And what we should recognize is that if I'm dividing two powers, again, with the same base, the base stays the same, and then we subtract the exponents. So the first one minus the second one, m minus n. Right? Again, we can put the note, have to have the same base. So you have to have the same base in order for these rules to work. So again, let's simplify and evaluate. 8 to the power of 6 divided by 8 to the power of 4. So we have powers with the same base we're dividing. So that means that I can subtract the exponents, 6 minus 4, I get 8 to the power of 2. I'm just going to scroll back up just because I want to keep my notations or my colors consistent. So I had red. So again, this is simplified. Then evaluated would be, okay, what is 8 to the power of 2? In this case, 8 times 8 is 64. So this is the evaluated form. For B, same idea, just represented a different way. Right? Remember, we talked before, this fraction just basically means divide. So negative 5 to the power of 7 divided by negative 5 to the power of 3. I have negative 5 to the power of 7 minus 3, which is negative 5 to the power of 4. That's my simplified form. Evaluated form, negative 5 to the power of 4. And I should get 625. Again, make sure you include the brackets. If you don't include the brackets, and I'm looking at my calculator right now, although you can't see it, I didn't include the brackets, but my calculator gave me negative 625. But I know that if I have negative times a negative times a negative times a negative, my answer should be positive. Right? So I know that my answer should be positive. The number or the value is not going to change, just the sign. Right? So make sure, though, if you don't recognize that, always put the brackets if they're there. Do not try to shortcut it and not put them in, because you might get the same number but a different sign, which would mean that it would be wrong. C and D, same idea. For C, 7 to the power of negative 1 divided by 7 to the power of 2. We subtract, so negative 1 minus 2. Always the first one minus the second one, just like you would add or subtract any numbers. Right? Even though the first one's negative, that's fine. I get 7 to the power of negative 3. Again, we want to write our power with positive exponents, so I have to flip the base. 1 over 7 to the power of positive 3. That 3 can apply to both parts. 1 to the power of 3 is 1. 7 to the power of 3 on the bottom, which I can then take one step further and say 1 over 343. So that is my evaluated form. D, again, D is one of those examples where we have values and powers. So again, I'm going to go through and highlight. I'm going to highlight my numbers, highlight my powers. It's going to be easier for me to differentiate between the two. And similar to when we multiplied and we focused on just keeping parts the same, I can do the same thing here. I can focus on the parts that are similar. So negative 12 and 6, those are two numbers. I can divide those two. So negative 12 divided by 6 gives me negative 2. Y to the power of 5 divided by y to the power of 2 would give me y to the power of 5 minus 2. So I get negative 2y to the power of 3. Again, the reason why we're allowed to do that, if I kind of look separately, right, just as an aside, negative 12y5 divided by 6y squared, I can actually rewrite this as just negative 12 over 6 times y to the power of 5 over y squared. Right? When we multiply fractions, we multiply across, so this is the same thing. I can just do my two numbers dividing, and I can do my two powers dividing, and then multiply the two answers together, which would give me negative 2y to the power of 3. So again, similar concept to what we were talking about. And again, I can't evaluate it any further. I don't know what y is, so I can't evaluate and say, well, this works out to 5 or 10 or a number, right? So I can't evaluate it any further. So my final answer here is my simplified and evaluated form. Oops. The last rule is the power of a power rule. So this is like an exponent on top of an exponent. So this one's going to be a little bit different in terms of expanding, but it's going to be the same kind of idea. Here it looks a little different because we only have one kind of power, but this power is raised to another power. So I have 5 to the power of 2 to the power of 3. So let's think about what that looks like expanded. Well, my base, I have two bases technically, the 5 and the 5 to the power of 2. I'm going to start with my largest base, or my largest power, which is the 5 to the power of 2 raised to the power of 3. So what that means is I have 5 to the power of 2 3 times. So I have 5 to the power of 2 times 5 to the power of 2 times 5 to the power of 2. If I want to expand that, well, 5 to the power of 2 means 5 times 5 times 5 to the power of 2. So let me color code this portion. 5 to the power of 2 times 5. So 5 times 5. And then multiplied by 5 times 5 again. Multiplied by 5 times 5 again. And if I want to simplify this expression now, it's just a string of 5s multiplied. I can rewrite that as 5 to the power of 3. Not 3, sorry. Wow. 5 to the power of 6. So I have 6 5s being multiplied together. let's take a look at the next expression, 2 to the power of 3 to the power of 4. So similarly to the one we just did, 2 to the power of 3 times 2 to the power of 3 times 2 to the power of 3 times 2 to the power of 3. So this one might be messy to write out. But essentially it's saying I have 4 groups of 2 to the power of 3 all multiplying each other. And if I expand this, I get 2 times 2 times 2 multiplied by 2 times 2 times 2 multiplied by 2 times 2 times 2 times 2 multiplied by third group 2 times 2 times 2. All of that simplified. So I look at this, I can write this as a power or a single power base 2 raised to the power of 12. And then lastly, the last expression, 8 to the power of 4 squared, means I have 8 to the power of 4 times 8 to the power of 4, which can be broken down into 8 times 8 times 8 times 8, 4 eighths, multiplied by another 4 eighths. And if I go through and simplify this as a single power, it's going to be 8 raised to the exponent of 8, because there's 8 eighths being multiplied. So again, my goal is to somehow create a shortcut going from the expression to the single power. Is there a way I can just quickly go through rather than having to expand it? And there is, and that rule states that when I have a power to a power, I keep the base the same as I've always done, and I multiply the exponents. Again, have to have the same base, and we're multiplying the exponents. And that is my shortcut for when I have a power to a power. So let's go through and evaluate, simplify and then evaluate. So 3 to the power of 4 to the power of 2. Power to a power tells me that I have to multiply my exponents, so 4 times 2. So I get 3 to the power of 8. Again, similar to before, this is simplified. Evaluate says, okay, tell me what does 3 to the power of 8 actually work out to? 6,561. So this is my simplified, or not my simplified, my evaluated form. For B, even though I have a negative base, the same rules still apply. Negative 10 squared to the power of 3, power of a power. So I have negative 10 raised to the power of 2 times 3. So negative 10 raised to the exponent 6. And on my calculator, negative 10 to the power of 6. Again, make sure you put it in brackets because we have a negative number. 1 followed by 6 zeros. C, again, same kind of concept. Power to a power, we keep the base the same. 4 to the power of 2 times negative 3. I get 4 to the power of negative 6. Negative power, I want to rewrite it as a positive. So 1 over 4 to the power of positive 6, which becomes 1 over 4 to the power of 6, because this 6 applies to both parts. But 1 to the power of anything stays as 1. And then evaluated, I get 1 over 4,096. For D, this is again a little bit different. This is now combining different components. We have a number. a 5. We have one variable or one power, a. We have another power with base b. And all of that is raised to a power of 2. So when you have something like this, the exponent on the outside applies to every single term. So what this actually works out to is 5 to the power of, and this would technically be a power to a power rule. If we don't see an exponent, we can assume it's 1. So this would be 5 to the power of 1 times 2 times a to the power of negative 2 times 2 times b to the power of 3 times 2. Simplified, 5 to the power of 2 is just 5 squared. A to the power of negative 2 times 2 is negative 4. And for b, 3 times 2 is 6. I can simplify this a bit further. 5 squared is 25. So a negative 4, b 6. But I have this negative exponent. And I want to turn it into a positive exponent. So if that's the case, normally we said we would flip the base. And in this case, what is the base? Well, the negative 4 is only attached to the a. So that means that I'm only going to flip the a power. So I'm going to leave the 25 and the b to the power of 6 on top. The a is going to go underneath. And now the exponent is positive. And if you're not quite sure why, just off to the side, if I did 25 times 1 over a, right, so if I just flip it 1 over a to the power of 4 times b to the power of 6, multiplying fractions, these are all whole numbers technically over 1, I still end up with 25b6 over a to the power of 4. So when I have only a portion that is negative, I can just move that portion underneath, create a fraction, and then the exponent can become positive. So this lesson is looking at the 3 different power laws. Now these are probably going to be new, so it is going to be very helpful if you practice and practice and practice, right? One question you might be able to get through, but you look at a different one, different base, different exponents, maybe there's a letter involved, right? Doing more practice allows you to become more familiar with the concept, so it makes it easier to understand and simplify and evaluate. So just make sure you just remember the 3 rules, take a look back over them, right? Power of a power, we multiply. Quotient or dividing powers, we subtract. And multiplying powers, we add. So those are the 3 rules in addition to the negative exponents and the 0 exponents that we looked at previously.